The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. The voice you selected does not support this language. Please click the upper right corner to switch to another voice. Sometimes science doesn't break with a bang. There are no explosions, no alarms, no dramatic press conferences. Just a quiet, slow, uncomfortable feeling that something is deeply wrong. This is one of those moments. For most of human history, the universe felt stable and predictable. Stars moved across the sky with quiet discipline. Galaxies followed elegant paths. Gravity behaved exactly the way our equations said it should. Everything made perfect sense. Until it didn't. It all started with a simple observation. Galaxies were spinning too fast. When astronomers measured how stars move inside galaxies, they expected a familiar pattern. Stars near the center should move quickly, and stars farther out should slow down. That's how gravity works, or at least that's how we thought it worked. But galaxies refused to cooperate. No matter how far out astronomers looked, stars just kept moving at incredible speeds. So fast, in fact, that these galaxies should have torn themselves apart long ago. But they hadn't. They were perfectly intact, calm, and stable. At first, scientists assumed the problem was simple. Maybe the telescopes were wrong. Maybe they miscalculated the distances. Maybe the math just needed a little tweak. Years passed. Better instruments were built. More and more galaxies were measured. And the problem didn't go away. It got bigger. It became clear that something invisible was holding these galaxies together. Something heavy, something massive, something that no one could see. This was the first quiet crack in our understanding, a subtle mismatch between what we expected and what reality showed us. The universe was already behaving in ways we were not ready for. Then came the galaxy clusters, huge collections of galaxies, all bound together by gravity. The exact same problem appeared again, but this time it was magnified. The galaxies inside these clusters were moving far too fast to be held together by the gravity of the visible matter alone. According to everything we could see, these clusters shouldn't even exist, but there they were, stable, ancient, and completely Gravity was pointing to something hidden. And gravity doesn't lie. Light can be deceiving, but gravity is honest. It responds to mass, whether that mass shines or not. When scientists finally managed to map gravity directly using a technique called gravitational lensing, they saw it with their own eyes. Vast regions of gravitational pull with almost no light coming from them. An invisible structure shaping the entire universe. This invisible presence became unavoidable. It wasn't just a convenient theory anymore, it was a requirement. And so, science did something it rarely does willingly. It accepted the existence of something it could unobserve directly. They gave it a name, dark matter. Not because it was evil or mysterious, but simply because it didn't interact with light. Dark matter doesn't glow, it doesn't reflect, and it doesn't absorb light. It passes through everything, including you and me, without leaving a single trace, and yet it outweighs all visible matter combined. All the stars, planets, gas, dust, and life in the universe make up less than 5% of everything. Dark matter is the dominant component. This realization changed everything. Galaxies were no longer just islands of stars. They were luminous decorations wrapped around vast, invisible halos of dark matter. Cosmic structure didn't form because matter just happened to clump together. Matter clumped together because dark matter told it where to go. The universe wasn't built from light. Light was just the surface. Dark matter was the skeleton. But this raised an even more unsettling question. If most of the universe is completely invisible to us, what else might we be missing? That question arrived at exactly the wrong time. Because just as scientists were beginning to accept the reality of dark matter, the universe delivered an even deeper shock. The expansion of the universe wasn't slowing down, it was speeding up. For decades, astronomers believed that the expansion that started with the Big Bang should gradually decelerate. Gravity, after all, pulls things together. It should have been applying the brakes on the cosmos. Instead, observations of distant galaxies revealed the exact opposite. They were accelerating away from each other, not because they were moving faster through space, but because space itself was stretching faster and faster over time. Something was pushing the universe apart. Something pervasive, uniform, and invisible. Something even more mysterious than dark matter. This force was given a name that explained absolutely nothing. Dark energy. Dark matter pulls. Dark energy pushes. Dark matter builds structure. Dark energy dissolves it. Together, they dominate the entire universe. And together, they were never part of the original plan. This is the moment cosmology truly changed. The universe was no longer just strange. It was fundamentally incomplete. Our most successful and cherished theories described only a tiny fraction of reality. The rest was dark, unknown, and unexplained. This realization wasn't frightening at first. It was humbling. Then it became unsettling. When scientists finally accepted that galaxies were behaving strangely, a deeper realization followed. The problem wasn't just in one or two places, it was everywhere. Every galaxy told the same quiet story. Every cluster of galaxies repeated the same contradiction. Stars were moving too fast. Galaxies were staying together when all our physics said they should be flying apart. Gravity was stronger than it had any right to be. At first, this felt like a simple measurement issue. Astronomy has a long history of mistaken distances and faulty assumptions. When something looks wrong, the safest, most logical explanation is human error. So, scientists recalculated. They built better telescopes. They refined their techniques. They observed the cosmos in different wavelengths of light, from radio waves to X-rays. Nothing changed. The universe remained stubborn, and slowly, reluctantly, cosmology crossed an invisible line. The problem wasn't with the observations. The problem was with reality itself. This is where gravity became the key. See, gravity doesn't care about light. It doesn't respond to how bright something is, what color it is, or how hot it is. Gravity responds to one thing and one thing only: mass. If something has mass, gravity feels it. If it doesn't, gravity ignores it. This makes gravity the most honest force in the universe. It can't be fooled by appearances. So astronomers began to use gravity itself as a measuring tool, not just by watching things move, but through something even more subtle and profound: gravitational lensing. According to Einstein's theory of general relativity, mass bends spacetime, and bent spacetime, in turn, bends the path of light. When light from extremely distant galaxies passes near massive objects on its way to us, its path gets curved. The images we see become distorted. Their shapes stretch into arcs. Sometimes, we even see multiple copies of the same galaxy. By studying these distortions, scientists could map the distribution of mass directly. They weren't just guessing based on starlight anymore. They were tracing the very geometry of space. And when they did this, the universe revealed something absolutely astonishing. Most of the mass was not where the light was. Galaxies appeared to be wrapped in enormous, invisible halos of mass. Clusters of galaxies were embedded in vast, unseen clouds. The entire luminous universe, everything we can see, was just sitting inside a much larger, darker structure. It was like seeing frost on a window, perfectly outlining an invisible framework we never knew was there. This invisible framework was everywhere. It shaped how galaxies formed in the first place. It dictated how clusters of galaxies assembled. It guided how all matter flowed along immense cosmic filaments. Without this unseen mass, nothing we see today would exist in its current form. It wasn't just some rare, exotic thing. It was dominant, and it behaved differently from the ordinary matter we know. It didn't clump together tightly. It didn't seem to collide or interact. It passed through itself as if it were a ghost. This strange behavior became incredibly obvious when scientists observed galaxy clusters colliding. When two galaxy clusters smash into each other, something fascinating happens. The hot gas, which makes up most of the visible, ordinary matter, slams together, slows down, heats up, and glows brightly in X-rays, but the invisible mass doesn't stop. It passes straight through the collision, leaving the glowing gas behind. Gravitational lensing maps showed two separate structures. The light from the hot gas was in one place, but the center of gravity was in another. This separation was unmistakable proof. It told us that this invisible mass wasn't just faint matter we couldn't see. It was something fundamentally different. This single observation convinced many skeptics. Dark matter was no longer just a convenient placeholder in an equation. It was a real, physical component of the universe, with measurable effects and predictable behavior. But we still had no idea what it actually was. This raised a deeply uncomfortable question. If this dark matter outweighs everything we can see by a factor of 5 to 1, why can't we detect it directly? Scientists built incredibly sensitive detectors deep underground, shielded from cosmic rays and any background noise. They waited patiently for a dark matter particle to bump into one of their atoms. Years passed. Nothing definitive appeared. Particle accelerators, like the Large Hadron Collider, searched for signs of new particles that could be dark matter. Astrophysical observations looked for faint signals of dark matter particles annihilating each other in space. Again, nothing conclusive. Dark matter was everywhere, and yet it was nowhere to be found. This absence of detection was frustrating, but it also taught us a lesson in humility. The universe was telling us something important. Reality does not guarantee accessibility. Just because something exists and shapes everything around us doesn't mean we guaranteed to be able to touch it or see it directly. Dark matter might only interact with our world through gravity, or so weakly through other forces that detecting it is just extraordinarily difficult. This possibility isn't very comforting. It means some aspects of reality may always remain indirect, understood only through their effects, not through direct contact. Yet, for all its mystery, dark matter solved a deeper puzzle. It explained how structure formed so quickly in the early universe. Right after the Big Bang, matter was spread out almost perfectly, uniformly. There were tiny fluctuations in density, but they were incredibly small. Ordinary matter, on its own, would have struggled to clump together. The intense pressure from radiation would have smoothed everything out. But dark matter changed the game. Because it doesn't interact with light or radiation, it could start clumping together much earlier. It formed invisible gravitational wells, like seeds of structure. Ordinary matter then fell into these pre-made wells. Stars ignited, galaxies assembled. Without dark matter, our universe would be a nearly empty, smooth, featureless void. There would be no galaxies, no stars, no planets, and certainly no life. Dark matter isn't just a minor detail. It's the foundational architect of the visible universe. This realization completely changes your perspective. The things we see, the brilliant stars and galaxies, they aren't the drivers of cosmic evolution. They're the outcomes. The light is just decoration on a structure that is fundamentally invisible. And once this mind-bending idea took hold, it led to an even more disturbing extension. If most of the mass in the universe is invisible, and most of the gravity comes from something we don't understand, then our certainty about anything disappears. We can't just assume we understand the universe simply because we can see parts of it. Reality becomes layered, where the surface appearances hide a deeper, unseen framework. This was the moment cosmology lost its innocence. Before dark matter, the universe felt explainable, like a puzzle we were close to solving. After dark matter, it felt provisional. Every explanation came with an asterisk. Every model came with a list of assumptions about the unknown. And then came another shock. Even dark matter wasn't the end of the story. Because as scientists refined their measurements of the cosmos, something else emerged, something even more unsettling. Dark matter explains why galaxies hold together. It's a cosmic glue. It pulls things together, but it cannot push things apart. Yet, observations showed that the expansion of the universe itself was accelerating, not slowing down under gravity's pull, not stabilizing, but actively speeding up. This meant another invisible component had to be at work, something that counteracted gravity on the largest possible scales, something smooth, uniform, and present everywhere. This was dubbed dark energy. So now we have two great unknowns: dark matter, which builds structure, and dark energy, which stretches space and threatens to eventually pull all that structure apart. Together, they dominate the universe. And together, they were never predicted by any of our early theories of cosmology. This is where the realization truly deepened. The universe isn't just missing a few pieces. It is dominated by the missing pieces. Only about 5% of the entire cosmos is made of the familiar matter that makes up you, me, the Earth, and all the stars. Everything else is dark, unknown, and unexplained. This isn't a small gap in our knowledge. It is the overwhelming majority of reality. At this point, cosmology stopped being about refining old ideas. It became an exercise in humility. The universe hadn't revealed its rules completely. It had revealed our own assumptions and was quietly dismantling them, one by one. This is difficult to accept because, as humans, we like completeness. We like closure. We like explanations that feel finished. But the universe doesn't offer that. It offers consistency without transparency. It shows us patterns without asking our permission. It presents truth without any obligation to make it easy for us to understand. Dark matter doesn't announce itself. It doesn't glow. It doesn't interact. It simply exists. This is a powerful lesson, not just philosophical, but physical. And this realization prepares us for what comes next. Because once scientists accepted the existence of invisible mass, they had to confront something even stranger. What if space itself isn't a passive, empty stage? What if space can stretch, store energy, and dominate the entire future of the cosmos? What if emptiness is not empty at all? To answer that, cosmology had to rethink the very nature of space, time, and expansion itself. And that leads us directly into part 3, where the universe begins to behave in ways that defy intuition completely. An empty stage, a silent, black background, where all the action happened. This idea worked just fine until the universe started acting strange again. This time, the problem wasn't inside galaxies, but between them. You see, when astronomers look far into the distance, they're also looking back in time. The light from those remote galaxies has been traveling for billions of years to reach us. Everyone expected a simple answer. The expansion should be slowing down. That's what our intuition told us. That's what the equations predicted. But the universe had other plans. In the late 1990s, two separate research teams made a quiet but absolutely earth-shattering discovery. The distant galaxies were farther away than they were supposed to be. The rate of expansion was actually speeding up over time. Something was pushing everything apart. At first, nobody wanted to believe it. It just seemed impossible. The teams double-checked their data. They questioned their calibrations. They hunted relentlessly for any possible error that could explain this bizarre result. But the conclusion held firm again and again. The universe was accelerating. This discovery didn't arrive with a big bang or a dramatic flash, but its implications were enormous. If the expansion is speeding up, it means that on the largest scales, gravity is losing. It was smooth, uniform, present even in the most desolate voids of space. In fact, the emptier the space, the more powerful this influence became. Scientists gave this unknown influence a name: dark energy. Dark energy wasn't discovered directly. It was inferred from the way the universe is moving. But here's a crucial distinction. It doesn't push objects asterisk through asterisk space. It stretches space itself. That difference is subtle, but it's profound. It means the universe has no center and no edge. The expansion is happening everywhere at once. No matter where you are, you'd see the same thing: distant galaxies receding from you in all directions. But dark energy doesn't dilute. Its density stays pretty much constant. Then, quietly, dark energy took over. And once it did, the future of the cosmos changed forever. In a universe dominated by dark energy, the formation of large-scale structures slows down. New galaxies stop forming. Clusters of galaxies stop growing. And over immense timescales, something lonely starts to happen. Galaxies will drift beyond each other's cosmic horizons. Light sent from one galaxy today will never reach another far-off galaxy. The mismatch between the predicted value and the observed value is the single biggest failure in the history of physics. Either our theory of vacuum energy is completely wrong, or our theory of gravity is incomplete, or both. This failure isn't embarrassing, it's a guide. Not because of any stuff in it, but just because that's what space asterisk does. Asterisk. If that's true, then emptiness isn't empty at all. It's an active, restless, creative medium with its own properties, its own energy, its own dynamics. This idea actually aligns with quantum physics, where empty space is a chaotic foam of particles and fields popping in and out of existence. And why is it only becoming dominant now, billions of years into the universe's life? Those universes would either expand too fast for any structures to form, or they'd collapse back on themselves instantly. No galaxies, no stars, no life. It's not a satisfying answer, but the universe isn't required to satisfy us. But this isn't the end of our story. Once we accepted that space itself is dynamic, that it can stretch, store energy, and dominate the entire universe, another question naturally came to mind. What about time? Is time as fundamental as we think? Or could it, too, be something that emerges from a deeper reality? Thanks so much for watching. If you're enjoying this journey into the mysteries of the cosmos, do forget to like this video. Once scientists accepted that space itself could stretch, store energy, and dominate the universe, a deeper question became unavoidable. If space is dynamic, what about time? For centuries, time was treated as absolute. It flowed forward at a steady pace, the same for everyone. That idea survived until Einstein. He showed that time bends. Clocks move differently depending on speed and gravity. Time slows near massive objects. Time slows for fast-moving observers. Time is not universal. But even after Einstein, time was still assumed to exist everywhere, a dimension stitched into reality, always present, always flowing. Then cosmology pushed further back, toward the beginning, and time itself began to feel fragile. When astronomers traced expansion backward, the universe shrank. Galaxies moved closer, matter compressed. Eventually, everything converged. Density approached infinity. Temperature exploded. This moment became known as the Big Bang, but that name is misleading. It was not an explosion in space. It was the expansion of space, from a state where our equations stop working. This is where time becomes problematic, because our understanding of time relies on change. Before the Big Bang, there was no space expanding, no clocks ticking, no motion. Asking what happened before the Big Bang may be meaningless, because before requires time, and time may not have existed yet. This idea is unsettling, not emotionally, logically. It challenges the grammar of thought. Questions like what caused the Big Bang assume time already existed. But if time itself emerged with space, then causality breaks down. Cause and effect lose meaning. The universe may not have begun in time. Time may have begun with the universe. This concept feels abstract, but physics forces it. When equations are pushed backward, time behaves strangely. Near the Big Bang, space-time becomes so curved that the distinction between time and space blurs. They swap roles. Coordinates lose identity. Everything becomes compressed into a state where classical descriptions fail. This is where general relativity reaches its limits, and quantum physics takes over. But quantum physics and gravity do not agree. At small scales, quantum mechanics dominates. Particles behave probabilistically, fields fluctuate, certainty dissolves. At large scales, gravity dominates. Space-time curves smoothly. Deterministic equations work beautifully. At the Big Bang, both are required, and neither works. This breakdown is not a failure. It is a signpost. It tells us our theories are incomplete. Something deeper is missing. Physicists have proposed many ideas to address this. Some suggest the Big Bang was not the beginning, but a transition. Perhaps our universe emerged from a prior state, a bounce, a collapse, followed by expansion. In such models, time extends beyond the Big Bang, but its behavior changes. Others suggest that time is emergent, not fundamental, like temperature. Temperature is real, but it emerges from particle motion. It is not a basic ingredient. Similarly, time may emerge from deeper, timeless processes. At the most fundamental level, reality may not include time at all. Only relationships, only correlations, only change without flow. In some quantum gravity models, the equations contain no time variable, none. The universe is described as a static configuration. Time appears only when observers inside it compare states. This is deeply counterintuitive, but mathematics does not care about intuition. If time is emergent, then the Big Bang was not a moment. It was a boundary, a region where classical time ceases to apply. This changes how we think about origins. The universe did not start. It transitioned into a regime where time makes sense. Before that, asking about earlier moments is like asking what is north of the North Pole. The question fails. This perspective also reframes cosmic inflation. Inflation proposes that very early in its history, the universe underwent a brief period of extremely rapid expansion, faster than today, much faster. This expansion smoothed out irregularities, explains why distant regions look similar, explains why space is nearly flat. Inflation fits observations remarkably well, but it raises its own questions. Inflation requires a specific energy field. It requires fine-tuning, and once inflation begins, it may never completely stop. In some regions, inflation continues, creating bubble universes, each with its own physical constants. This leads naturally to a multiverse, a landscape of possible universes, most lifeless, some stable, a few complex. In this picture, our universe is not special. It is selected, not by design, but by survivability. This again makes time feel less fundamental. If universes constantly bud off from an inflating background, then beginning loses meaning. There is no single start, only local transitions. Our observable universe began when inflation ended here. Elsewhere, different histories unfolded. Time becomes local again, relative not just to motion, but to cosmic region. This idea is not philosophical speculation. It arises naturally from equations. Whether it is correct remains unknown, but it fits the data disturbingly well. Yet even inflation does not escape deeper problems. It still requires initial conditions. It still assumes a pre-existing framework. It still pushes the question back. Why inflation? Why those conditions? Why that structure? At some point, explanation stops. Not because we choose to stop, but because meaning dissolves. This is where cosmology brushes against something profound. The universe may not have a reason. It may simply exist, not for a purpose, not with intent, but as a self-consistent structure. Physics seeks laws, not motives. Time, in this context, becomes a tool, a coordinate, a convenient way to describe change, not an absolute river flowing from past to future. This challenges human intuition deeply. Because our consciousness is tied to time, memory defines past, expectation defines future. Identity exists in flow. If time is emergent, then consciousness itself is emergent. Experience arises from ordering, from correlation, from structure, not from a fundamental arrow. Yet despite all this abstraction, the universe still behaves consistently. Entropy increases, structures age, stars burn fuel, clocks tick. The arrow of time exists, but its origin is mysterious. Why does entropy increase? Why did the universe start in a low entropy state? Why was order present at all? These questions remain open. They connect cosmology to thermodynamics, to information theory, to quantum mechanics, and possibly to consciousness. But science has not crossed that bridge yet. What we know is this: Time behaves normally now, but it may not have always done so, and it may not behave normally forever. As the universe expands, entropy increases, energy spreads, structures dissolve. In the far future, time may lose meaning again, not because it stops, but because nothing changes. A universe with no gradients, no motion, no events. Time without events is indistinguishable from no time at all. This is the quiet ending implied by dark energy, a cold, dilute universe. Stars extinguished, black holes evaporated, particles drifting endlessly. Change slows toward zero. Time fades not with a bang, but with silence. Yet before that distant fate, something remarkable happened. Complexity arose against entropy, against probability. Matter organized, life emerged, observers appeared, and those observers began asking questions. The universe became aware of itself. This is not mystical, it is physical. Brains are matter. Thought is process. Awareness is structure. And structure exists only because the universe allowed it. That allowance may be temporary, but it is real. And it leads us to a question that reshapes everything. If time emerged, if space is dynamic, if the universe began without guarantees, then how did structure manage to form so precisely? Why galaxies? Why stars? Why planets? Why not chaos? To answer that, we must look at the architecture of the universe itself, the large-scale structure, the cosmic web, and the invisible scaffolding beneath it. That journey begins in Part 5. Filaments of matter, hundreds of millions of light years long, weave through space. Galaxies aren't just floating freely in the void. They're strung along these invisible highways of mass. The giant clusters we see sit at the cosmic intersections, the bustling cities where filaments cross and matter piles up. This grand architecture wasn't designed by some cosmic architect. It emerged naturally, sculpted by gravity, acting on tiny, almost imperceptible irregularities in the very early universe. The pressure from radiation in the early universe would have resisted its collapse. The universe would be a much more chaotic, unstructured place. Gas streamed along these dark matter pathways, like morning fog rolling into valleys on Earth. Where these streams of gas met, galaxies were born. This realization reframes everything. Our own Milky Way isn't an isolated island. It resides within a filament known as the local sheet. This sheet connects to larger structures, which connect to even larger ones, all the way up to superclusters and patterns so vast we can barely comprehend them. Our position in this cosmic tapestry isn't special or central. Scientists can test this idea with powerful computer simulations. When they create a virtual universe with only ordinary matter, the simulation fails to produce the structure we observe. But when they add dark matter into the mix, something incredible happens. Filaments emerge, clusters form, voids empty out. They're stripped of their gas, their star formation fizzles out, and they tend to become smooth, elliptical galaxies. But galaxies in the calmer filaments can grow steadily, feeding on flows of cold gas that allow them to maintain their beautiful spiral structures. And galaxies stranded in the voids remain small, isolated, and underdeveloped. A galaxy's environment is its destiny, and that environment is dictated by the cosmic web. Their rotation isn't random. It's a kind of inherited memory from the large-scale flows of matter that formed them billions of years ago. Their fates are largely determined by their position in the web. Yet, within these constraints, incredible complexity flourishes. We can even map this invisible web. And remarkably, these maps match the predictions from our simulations, another quiet victory for cosmology. But the web still hides deep mysteries. On the very largest scales, the universe should become smooth and uniform, and for the most part, it does. Each filament traces a line of gravitational memory back to the beginning of time. the galaxies, the stars, the planets, and us. This unbroken chain of cause and effect connects the largest scales to the smallest. If the initial conditions had been slightly different, the web would be different, and the history of the universe would have been rewritten. The universe, through us, has developed eyes, and this leads to the most profound question of all. If the universe is a web of interconnected structures, and if observation itself is a process happening within that web, does the act of measuring reality actually change it? To even begin to answer that, we must leave the vastness of cosmic scales and descend into the strange and uncertain world of the quantum realm. Thanks for watching. If you enjoyed this journey through the cosmos, be sure to follow for our next chapter to figure out if observation really matters. Physics had to go somewhere pretty uncomfortable, downward, not into smaller machines, but into smaller truths. You see, at the very smallest scales, the universe doesn't behave like the one we experience every day. It doesn't move smoothly. It doesn't follow our intuition. It doesn't even agree to exist in just one state at a time. This is the wild world of quantum mechanics. And in this world, certainty completely falls apart. Particles aren't little points. They're clouds of probability. A particle doesn't have a specific position. It just has a likelihood of being found somewhere. It doesn't have a single momentum. It has a whole range of possible momenta. Reality isn't actually defined until it's measured. And I don't mean that as a metaphor. This is proven by experiment. The most famous example is the double-slit experiment. Imagine you send particles, like electrons, toward a barrier with two slits in it. You get an interference pattern on the screen behind the barrier, as if each particle somehow passed through both slits at the same time. Now, here's the crazy part. Do the exact same experiment, but this time, place a detector to see which slit each particle goes through. The moment you observe it, the wave behavior vanishes. The particle picks a slit. The interference pattern disappears. Nothing else changed. Same setup, same particles. The only difference was observation. Reality itself responded. This isn't some philosophical thought experiment. It's been verified countless times with electrons, photons, atoms, and even large molecules. The universe behaves differently when it's being watched. This is deeply unsettling because it suggests that measurement isn't a passive act of looking. It's participatory. The act of observing doesn't just reveal reality. It helps create it, at least on a local level. Physicists have spent decades arguing about what this all means. Some say observation causes the wave function of possibilities to collapse into a single reality. Others propose that all possibilities actually happen, branching off into parallel universes. Some even wonder if consciousness itself is involved. And then there are those who say we don't need an interpretation. we just need to do the math. But no matter which interpretation you prefer, the effect is real. Observation matters, at least at small scales. So, this brings up an unavoidable question. Does this effect scale up? Does the entire universe care that it's being observed? I don't mean by humans specifically, but by any system capable of measurement. Stars measure gravity. Atoms measure fields. Every interaction is a form of measurement. This way of thinking suggests measurement isn't special. It's fundamental and happening everywhere all the time. This completely reframes our picture of reality. The universe isn't some static object just waiting for us to discover it. It's an ongoing process, constantly being defined through interaction, through relationships, through participation. The cosmos is less like a giant machine and more like a conversation. Not a conversation with intent or purpose, but one built on constant feedback. At the quantum level, outcomes aren't fixed. They're constrained by rules and probabilities, but the specific results only emerge when interactions happen. This isn't just random chaos. It's a kind of structured uncertainty, and this uncertainty is essential. Without it, atoms would collapse, stars wouldn't be able to shine, and chemistry as we know it wouldn't work. Quantum uncertainty is what gives the universe stability. It's what allows electrons to settle into stable orbitals around an atom instead of spiraling into the nucleus. It prevents everything from collapsing into nothing. So, at the smallest scales, uncertainty actually creates order. It's counterintuitive, but it's real. And this uncertainty might just connect to the grand scale of the cosmos. In the very early universe, there were tiny quantum fluctuations, minuscule variations in energy. They were barely noticeable. But then, a period of rapid expansion called inflation stretched them out to astronomical sizes, freezing them into the fabric of space itself. Those tiny quantum jitters became the seeds of large-scale structures. They grew into the vast filaments and clusters of galaxies we see today. They grew into you. The entire cosmic web can be traced back to quantum noise. Not chaos, but noise that follows rules. This means the largest structures in the universe grew directly from its smallest uncertainties. This connection is profound. It links the quantum world to the cosmos, the smallest scales to the largest, uncertainty to structure, and measurement to meaning. It suggests that the universe isn't deterministic in the classical sense. If you could rewind and start again with the exact same initial conditions, you could get a different outcome. Which outcome occurs depends on interaction, on context, on measurement. But this doesn't mean the universe is totally unpredictable. It's statistically stable. Patterns emerge, averages hold true, and physical laws apply. It's just that the specifics can vary. This is why cosmology works as a science, but also why it constantly surprises us. Our predictions are based on probabilities, not absolutes. This framework changes how we think about destiny. Galaxies don't have a fixed fate. They have a range of likelihoods. Stars don't have a guaranteed future. They have probabilities. Even the universe itself doesn't have a single locked-in ending. We see evidence for a cold, empty future driven by dark energy. But if dark energy changes over time, the whole story changes. Nothing is written in stone. This uncertainty doesn't weaken science, it strengthens it. Science is about building models, not declaring absolute truth. Our models are approximations of reality, and no single model captures everything. Quantum mechanics is incredibly accurate, but it feels incomplete. General relativity is powerful, but it doesn't play nicely with quantum rules. Cosmology tries to bridge them both and feels the tension. And this tension is what drives discovery. The universe resists simple explanations, and in that resistance, it reveals its depth. Now, let's go back to observation. In quantum physics, you don't need a conscious mind to make an observation. A simple particle detector is enough. Any interaction that creates an irreversible record counts as a measurement. This means the universe is constantly observing itself. Particles interact, fields exchange energy, and systems become definite. There's no observer standing outside of it all. Everything participates. This idea dissolves the notion of a detached universe we can study from the outside. There is no outside. Every measurement we make is internal to the system. This has huge implications for cosmology. We can't observe the universe from an external vantage point. We are inside it. This limits our certainty. We can't rewind the clock. We can't rerun the experiment. And we can't compare our universe with an alternative. We only get to see one history, one outcome. This is why cosmology can sometimes feel philosophical, but it's not philosophy. It's physics pushed to its absolute limits. This also affects how we think about the beginning. If quantum fluctuations shaped the early universe, then the Big Bang wasn't a perfectly smooth, orderly event. It was noisy, and that noise mattered. It seeded everything. This suggests the universe has always existed in a state between perfect order and perfect chaos. It exists on the edge of complexity. Too much order, and you get a rigid, dead universe. Too much chaos, and nothing stable can form. Complex systems, like life, thrive in that delicate balance in between. The universe seems finely tuned to exist on this edge. Again, this feels improbable, but we exist because the conditions were right for us to exist. This is an uncomfortable thought, but it's a consistent one. Quantum mechanics also introduces something called non-locality. When two particles are entangled, they remain connected no matter how far apart they are. If you measure a property of one particle, the other one instantly reflects that measurement. This doesn't send information faster than light, but it does mean reality isn't strictly local. Parts of the universe are linked in ways that defy our normal understanding of space. This isn't just a theory. It's been tested and proven over and over. Entanglement is real. This challenges the idea that the universe is just a collection of independent parts. It hints at a deeper unity, a holistic foundation where the very idea of separation is something that emerges, not something that's fundamental. This aligns with other mind-bending ideas that space, time, and separateness might all be emergent properties. The universe may be, at its core, fundamentally relational. Structure arises from relationships, not from isolated objects. This is a radical shift in thinking, but it's one supported by both math and experiment. This relational view helps explain why the universe feels so coherent. Despite the vast distances, the constant expansion, and the cosmic isolation, the underlying rules connect everything. The fabric remains unified. Now, the question becomes unavoidable. If reality is probabilistic, if observation matters, and if structure emerges from uncertainty, then what about us? What is our role in all of this? Are we just passive witnesses, or are we active participants? Does our consciousness matter, Or is it just another complex physical process? Physics gets a little quiet here, mainly because we don't have a good scientific definition of consciousness. But the question sticks around, not because it's mystical, but because observation is so central to the physics. Some interpretations of quantum mechanics say observers are crucial. Others insist they're not. But they all agree on one thing: measurement changes outcomes, and measurement is happening all the time. This means the story of the universe isn't finished. It's being written right now. Every interaction adds another line. Every observation collapses another possibility. The future is open. It's constrained by physical laws, but it is not fixed. This openness even applies to the fate of the cosmos. We don't know everything, and that ignorance is an honest reflection of reality. The universe has no obligation to make sense to us, but it does allow us to understand parts of it, and that's enough for us to keep going. From here, the path forward becomes a little clearer. If uncertainty and observation shape reality, then the next question is about boundaries. What can be known? What is observable? And where does information stop? Because the universe has limits. It has horizons, edges, not of space, but of knowledge. They are all equally real, but they can never communicate with each other. It sounds extravagant, but mathematically, it's actually simpler than the alternative. It gets rid of the tricky problem of why observation is so special. Instead of a reality that collapses, we get a reality that constantly, endlessly splits. We only experience one path because we are part of that path. This idea was, and still is, deeply controversial. But then, cosmology, the study of the entire universe, made it much harder to ignore. Our leading theory for the universe's explosive birth, cosmic inflation, has a strange feature. If it happens once, it might happen forever. While inflation stops in our little pocket of space, allowing galaxies to form, it continues raging on in the vastness beyond. This process, called eternal inflation, would constantly create new bubble universes. Each bubble would cool down, expand, and develop its own spacetime, perhaps even its own physical laws and constants. In this cosmic foam, our universe is just one bubble among countless others. We're not special, just lucky enough to be in a bubble that can support life. Most other bubbles might be empty, chaotic, or collapse in an instant. This brings us to a concept called the anthropic principle. It sounds complicated, but it's simple. We shouldn't be surprised to find ourselves in a universe with laws that allow for our existence. It's a selection effect. If the laws were different, we wouldn't be here to ask the question. In a multiverse, this isn't just a philosophical statement. It becomes a powerful predictive tool. If every possibility exists somewhere, we can only make statistical predictions about what an observer like us is likely to see. This is a huge shift in thinking for physicists, who usually prefer unique, elegant answers. The equations don't promise a single universe. They allow for a multitude. Take dark energy, the mysterious force accelerating our universe's expansion. Its measured value is incredibly fine-tuned. If it were much larger, galaxies would never have formed. If it were smaller, the universe might have collapsed back on itself. Why is it in this tiny, life-friendly range? A multiverse offers an answer. There are universes with all sorts of values for dark energy. But we could only ever exist in one where the value is just right. But this raises a huge problem. How do you test a theory about universes you can't see? This is where the scientific debate gets intense. Some argue that an untestable idea isn't science. Others say indirect evidence is what matters. We can't see the Big Bang or dark matter particles directly, but we infer their existence from the evidence they left behind. The multiverse might be similar. Its signature could be subtle, hidden in the statistical properties of our cosmos. For instance, if our bubble universe ever collided with another, it might have left a faint bruise on the cosmic microwave background, the afterglow of the Big Bang. Astronomers have looked for these cosmic bruises, and while there have been a few tantalizing hints, there's no definitive proof yet. Finding such a signal would be one of the greatest discoveries in history, confirming that our universe is not alone. Even without proof, the multiverse idea changes our entire perspective. We are not at the center of existence. We are not unique. We are simply residents of one small region in a structure so vast it defies imagination. It even redefines the concept of a beginning. In an eternally inflating multiverse, there might be no single moment of creation. Instead, there are countless local beginnings, as new bubble universes constantly pop into existence. The question, why is there something rather than nothing, dissolves. In this picture, there's always something, somewhere. This can feel diminishing, like we're just one insignificant outcome among trillions. But it can also be liberating. It means that meaning doesn't come from being special or unique. It comes from experience, from consciousness, from the relationships we build within our own slice of reality. Every branch has meaning for the beings within it. This forces us to be humble. It dissolves the hope for final, absolute answers and reminds us that the universe isn't obligated to be simple or intuitive. It only has to be consistent with itself. It also makes the existence of life even more remarkable. Life isn't a cosmic destiny. It's a fragile, temporary, and localized pattern that emerged against incredible odds. It is an emergent property that depends on a precise and delicate balance of physical laws and conditions. And so, the multiverse, whether real or not, forces us to zoom back in. From the dizzying scale of infinite universes, we return to our world, our galaxy, our star, and our planet. We are reminded that we exist in a thin, precious window where the chaos of the cosmos briefly gave way to order, complexity, and life. The quest to understand our place in the cosmos continues, but the multiverse has shown us that the cosmos itself might be infinitely grander than we ever dared to dream. Thanks for watching. If you found your mind expanding, be sure to like this video and subscribe for more journeys into the biggest questions in science. If the universe allows for many different outcomes, then life isn't a guarantee. It's conditional, it's fragile, it's bound to an incredibly narrow window of physical circumstances. When we zoom back in from the vast cosmic scales, the very first requirement becomes obvious: stable structures. Without galaxies, there are no stars. Without stars, there are no heavy elements. And without heavy elements, there's no chemistry worth mentioning. Hydrogen and helium alone just can't build complexity. They're too simple. Life, as we know it, needs carbon, oxygen, nitrogen, phosphorus, iron. These elements weren't there at the beginning. They are forged deep inside stars. Stars are the universe's cosmic factories. Through nuclear fusion, they turn simple atoms into heavier ones. But not all stars are created equal. Small stars burn slowly and quietly, making some elements. Large stars, however, burn fast and violently. They create many elements, and then they explode. These supernovae scatter enriched material across space. This cosmic enrichment is absolutely essential. Without it, planets like Earth simply could not form. This means life requires multiple generations of stars. The very first stars were massive and short-lived. They lived fast, died young, and polluted the early universe with the raw materials for complexity. Only after they had done this could complex chemistry even begin. This simple fact already limits when life could start. Too early, and the universe lacked the necessary ingredients. Too late, and the stars begin to fade. Life seems to emerge in a kind of cosmic middle age, not at the beginning and not at the end. Then there's the matter of planetary architecture. A planet has to be solid. It can't be too massive, or it becomes a gas giant. It can't be too small, or it loses its atmosphere to space. It must orbit its star at just the right distance. Too close, and any water evaporates. Too far, and it freezes solid. This region is often called the habitable zone, but that term is a bit misleading. Habitability isn't just a simple ring around a star. It's a complex intersection of many factors. The composition of the atmosphere matters. The presence of a magnetic field matters. Plate tectonics matter. The stability of its orbit matters. Even having a large moon, like our own, might be crucial. Earth's moon stabilizes our planet's axial tilt. Without it, our climate could swing chaotically between extremes. Life struggles to survive in chaos, and then we have to consider the star itself. Many stars are hostile. They flare violently, blasting their planets with intense radiation. Red dwarfs, the most common type of star in the galaxy, are notorious for this, potentially stripping the atmospheres from any nearby worlds. Life near them would have to find a way to adapt or hide. Sun-like stars are actually rarer. The short-lived massive stars die too quickly for complex life to evolve. The long-lived small stars might be too active in their youth. Once again, life seems to occupy a very narrow band of possibility. Next, there's chemistry. Carbon is special. It forms long, complex chains, and no other element comes close to its versatility. This isn't just a random fact. It's a consequence of its quantum structure, its electron shells, its bonding angles, its energy levels. The properties of carbon are finely tuned. Scientific models have shown that if you were to slightly change the fundamental constants of physics, carbon-based chemistry would fail. Life's window of opportunity narrows even further. And then there's water. Water is an extraordinary substance. It dissolves other substances. It buffers temperature, and it has the strange property of expanding when it freezes. This allows ice to float, protecting the ecosystems in the liquid water below. Again, these properties aren't generic. They arise from hydrogen bonding, a direct result of quantum behavior. If you tweaked the physical parameters slightly, water would lose its magic. Life would become much harder, or perhaps impossible. All of this suggests that life is not inevitable. It is allowed, but only under a precise set of conditions. This doesn't imply a designer. It implies constraint. Physics only permits complexity to arise in these narrow, specific regimes. We just happen to live in one of them. This realization reframes the entire question. Life isn't surprising because the universe is fine-tuned for it. Life is surprising because it exists at all. given the incredibly narrow constraints it has to work within. Now, let's consider time again. Life requires stability over billions of years. Stars must shine steadily. Planets must maintain stable climates. Catastrophic events must be rare. Things like giant asteroid impacts, gamma-ray bursts, or nearby supernova. If they happen too frequently, life is constantly being reset. If they're too rare, evolution might stagnate. It's all about balance. Earth's own history reflects this. We've had mass extinctions, but they weren't so frequent that they wiped the slate completely clean. They pruned the tree of life. They didn't chop it down. Evolution seems to need some disruption, but not total annihilation. And this balance is incredibly delicate. Then we have evolution itself. Life begins simply, but for complexity to emerge, it needs a lot of time. Random mutation alone is not enough. Natural selection matters. The environment matters. Feedback loops matter. Evolution is not a straight line marching towards progress. It's a branching, exploratory process. Most of those branches fail. Only a few persist. And intelligence is by no means a guaranteed outcome. On Earth, life existed for billions of years before complex brains appeared. And as far as we know, that kind of intelligence has only appeared once. This strongly suggests that intelligence is contingent, not inevitable. Given slightly different conditions, Earth might have remained a world of microbes forever. This is a critical point. Simple life may be common in the universe, but complex life could be rare. And technological civilizations might be rarer still. This is the core of the great filter idea, the theory that some step in the chain from non-life to advanced civilization is extraordinarily unlikely. We just don't know which step it is. Is it the origin of life itself? The jump to complex cells? The evolution of multicellularity? The emergence of intelligence? Or is it the final step, developing technology and surviving it? We don't know. This uncertainty hangs over our search for extraterrestrial intelligence. We look out at the stars, we listen for signals, we scan the skies, and so far we have found only silence. This silence could mean many things. Maybe life is rare. Maybe intelligence is rare. Maybe technological civilizations are very short-lived. Or maybe we're just early to the party. Or perhaps we're just not listening correctly. The universe isn't giving us an answer just yet. But this silence adds weight to the idea of our own fragility. If intelligence is a rare phenomenon, then its persistence really matters. Civilizations face hazards, both internal and external. They have to learn to navigate their own technology without self-destructing. They have to manage their resources. They have to avoid extinction. This might not sound like cosmology, but it's all connected. A civilization's survival depends on the stability of its planet, which depends on the behavior of its star, which depends on its galactic environment, which in turn depends on the large-scale cosmic web. Everything connects in a nested hierarchy of dependencies. Life is not an isolated miracle. It flows from quantum fluctuations at the dawn of time to the great cosmic filaments, to galaxies, to stars, to planets, to chemistry, to biology, and finally, to consciousness. If you break that chain at any point, life fails. This chain also suggests rarity, not necessarily uniqueness, but scarcity. And that makes the act of observation incredibly precious. You see, life is how the universe sees itself. I don't mean that metaphorically. I mean it literally. Our eyes are made of matter. Our brains are physical processes. Our thoughts are governed by the laws of physics. When life observes the cosmos, the universe is, in a very real sense, observing itself. This isn't mystical. It's reflexive. Observation is a physical process, and all physical processes are part of the universe. So awareness is a kind of local loop, the universe reflecting on its own structure. This doesn't grant us some grand cosmic purpose, but it does grant us perspective. Meaning emerges locally, not cosmically. Life isn't the goal of the universe, it's an outcome. A temporary, fragile, yet profound outcome. This perspective also reframes our future. If life is rare, then preserving it matters. Not because the universe demands it, but because nothing else will. The universe is indifferent. Entropy increases, stars fade. Dark energy continues to stretch space apart. Life must actively persist, or it will vanish. This is a sobering thought, but it's also empowering. Meaning isn't handed to us. It's something we create. This brings us back to the big picture. The universe allows complexity, but it doesn't protect it. Life arises, but it isn't guaranteed to last. Awareness flickers into existence, and then it may disappear. Unless it learns, unless it adapts, unless it understands its own context. Cosmology isn't some abstract field of study. It informs our very survival. It helps us understand the hazards, the timescales, the probabilities. Our place in the cosmos is not central, but it is an informed one. We live at a precious moment in time when life exists, when knowledge is possible, and when the universe is still observable. This is not an eternal state of affairs. It is a phase, and all phases eventually end. This leads us to the final, ultimate question of direction. Does the universe have an arrow? Is it moving toward something, or is it simply unfolding according to its laws? To answer that, we must confront the concept of entropy directly, not just as a measure of disorder, but as a glimpse into our cosmic destiny. There is one rule the universe never breaks. Everything moves forward, not in space, but in time. Stars are born, they burn, and they fade. Planets cool, mountains erode, memories form, and then slip away. We feel this direction constantly, this unstoppable flow from past to future. Yet, when physicists look at their most fundamental equations, something strange appears. Most of these laws don't care about the direction of time. You can reverse them, and they still work perfectly. Motion can run backward, forces remain valid, and interactions don't complain. But reality doesn't reverse. This glaring contradiction has a name: the arrow of time. To understand it, science turned to a concept called entropy. You've probably heard entropy described as disorder, but that's a bit misleading. Entropy is really about possibility. It's a measure of how many different microscopic arrangements can create the same macroscopic state. Low entropy means very few arrangements are possible. High entropy means there are many. And here's the key: systems naturally move from fewer possibilities to more. Not because they're forced to, but simply because it's overwhelmingly more likely. Think of a brand new deck of cards, perfectly ordered. That's one specific configuration. Now, shuffle it. The result is a jumbled, disordered deck. Why? That initial state is astonishingly special. There are vastly more disordered states than ordered ones. And yet, for some reason, the universe began in this highly ordered state. This is the deepest mystery of time. Why did the universe start with such low entropy? No known physical law required it. It just happened. And because it happened, time gained its direction. As the universe evolves, its total entropy increases. The early universe was hot, dense, and smooth. Then it expanded, and its entropy increased. But here's where it gets counterintuitive. In most systems, being uniform and spread out means high entropy, like gas filling a room. But when gravity is involved, the rules flip. For gravity, uniformity is a low entropy state, clumping things together, like forming stars and galaxies from a smooth cloud of gas, actually increases entropy. This flips our intuition on its head. The early, smooth universe had low gravitational entropy. As matter clumped together to form the cosmic structures we see today, the total entropy of the universe went up. So, the formation of complexity didn't violate the arrow of time, it drove it forward. This explains how complex things, including life, can arise even while the universe as a whole becomes more disordered. Life doesn't violate the second law of thermodynamics. It's a perfect example of it. Living systems are masters at accelerating entropy. We take in low entropy, high-quality energy, like sunlight or food, and we release high-entropy waste, like heat. We are engines of transformation, increasing the universe's total entropy faster than inert matter ever could. Entropy isn't just destruction. It's transformation from concentrated to diffuse, from structured to uniform, from potential to exhaustion. So what about the distant future? If the current model of cosmology holds, the expansion of the universe will keep accelerating. Galaxies will drift apart until they are lost from view. Star formation will slow down and eventually stop. Existing stars will burn out, leaving behind cold white dwarfs, neutron stars, and black holes. And even those won't last forever. Over unimaginable timescales, even black holes will evaporate through a process called Hawking radiation. Slowly, incredibly slowly, but inevitably. After an almost infinite amount of time, all that will be left is a cold, thin, nearly uniform soup of radiation. Entropy will have reached its maximum. This state is called the heat death of the universe. Time itself will lose all meaning, not because clocks stop, but because there will be no process left to mark its passage. Of course, this isn't the only possible future. We don't know the ultimate fate of dark energy. It could change, leading to a different outcome, but all scenarios are governed by entropy. This brings us back to our place in the cosmos. We exist in a very narrow window of time. We're here long after the Big Bang created the heavy elements we're made of, but long before the last stars fade away. We are early enough to still see the cosmic microwave background, the afterglow of creation, but late enough to have developed the science to understand it. This timing is remarkable. It doesn't imply a grand purpose, but it does imply a profound opportunity. Even the simple act of observing the universe participates in this process. Every measurement we take, every piece of information we record, requires an irreversible process that increases entropy. Knowledge costs energy. We aren't just passive observers. We are active participants in the cosmic story. This doesn't give us some special power, but it does give us a kind of responsibility. The arrow of time is not our enemy. It's the precondition for our existence. Without it, nothing would ever happen. There would be no stars, no chemistry, no evolution, and no thought. We can't reverse it. We can only move with it, navigating its flow, creating brief, beautiful pockets of local order. The fact that these moments are brief doesn't reduce their value. It creates it. So if everything fades, if all knowledge is temporary, and all observers are fleeting, what remains? That question leads us to what physics now considers the most fundamental thing of all, not matter. Not energy, but information itself. Thanks for watching. If you found this journey through time and entropy fascinating, consider subscribing for more explorations into the biggest questions in science. After entropy reframed time and destiny, physics took a surprising turn. This idea emerged slowly from black holes of all places. Black holes were once thought to be cosmic erasers. Anything that crossed the event horizon was lost forever. Its mass was added to the black hole, and its charge and spin remained measurable, but all other details were gone. This troubled physicists because it violated a core principle of quantum mechanics. Information must be preserved, not duplicated, not destroyed, preserved. This conflict became known as the black hole information paradox. If black holes destroy information, then quantum mechanics is wrong. If quantum mechanics is right, then black holes must somehow preserve information. Black holes do not destroy information. They encode it, but not where we expect it. The event horizon itself, once thought to be a featureless boundary, became the star of the show. It carries the information, not inside the black hole, but on its surface. This led to the holographic principle, a truly radical idea. It suggests that all the information contained within a volume of space can be represented on its boundary, just like a hologram. This isn't a metaphor, it's a mathematical equivalence. In certain models of spacetime, a universe with gravity is exactly equivalent to a universe without gravity living on its boundary. This has been tested and verified in specific cases, and it works, which is deeply unsettling because it suggests that space itself might be emergent, not fundamental. If the universe can be described entirely by information on a boundary, then the interior is secondary. Reality becomes informational. Space-time becomes a derived concept. This idea resonates powerfully with quantum mechanics. Particles are defined by their states. and states encode information. Interactions between particles are exchanges of information. The universe evolves by updating this information. From this perspective, matter isn't fundamental. Fields aren't fundamental. Even space-time isn't fundamental. Information is. This reframes everything. Entropy becomes the spread of information. Time becomes the flow of information. Observation becomes the acquisition of information. Memory becomes the storage of information. Even our identity becomes a specific informational pattern. This doesn't reduce reality to a mere abstraction. It grounds it. Information is physical. A principle from physicist Rolf Landauer shows that erasing information requires energy. Information has a thermodynamic cost. It's not just bookkeeping, it's real. Let's go back to black holes. As they evaporate through Hawking radiation, they slowly emit particles. Initially, this radiation appears random, but if information is preserved, subtle correlations must exist between the particles. Over immense stretches of time, this radiation encodes all the information of whatever fell in the black hole, becomes an information processor, not a destroyer. This process is incredibly slow, but, in principle, it's reversible. This resolution preserves quantum mechanics, but it comes at a price. Our intuitive notion of locality breaks down. Information stored on the horizon affects the interior, meaning the inside of the black hole depends on its boundary. Space-time geometry becomes secondary. This all suggests that our intuitive picture of space is incomplete. What we experience as a three-dimensional reality may be a projection, not an illusion, but a reconstruction from deeper informational rules. Space may be emergent, time may be emergent, and now matter joins them. This isn't nihilism, it's unification. Physics is always searching for the simplest, most minimal foundations, and information provides that. But what is information without interpretation? Bits of data mean nothing without context, without states, without relationships. Information is relational. It exists between systems. This perfectly matches the weirdness of quantum entanglement, where entangled particles share information non-locally. Their states are defined together, not separately. This again suggests that information isn't local, it's global and distributed, just as holography implies. This also reframes the arrow of time. The increase of entropy is simply information dispersing. The early universe had low entropy, meaning its information was highly concentrated. As the universe evolves, that information spreads out, becoming harder to access. It's not destroyed, just diluted. This dilution makes reconstructing the past practically impossible, but not theoretically forbidden. It explains why the past feels fixed. Its information is encoded in countless records, and why the future feels open. Its information is not yet correlated. Now, let's consider consciousness. If reality is informational, consciousness may be too. Our brains are magnificent information processors. Consciousness might be an emergent property of this complex information processing, not something magical or external, but physical. This doesn't solve the hard problem of consciousness, but it gives it a place to live. Awareness becomes a pattern, a dynamic informational loop that exists only under specific conditions, a flow of energy, a gradient of entropy, and structural stability. When those disappear, awareness fades. This is consistent with cosmology. As the universe's entropy increases, complex information processing becomes harder and eventually impossible. Awareness is temporary, but that doesn't make it meaningless. Meaning is local. Information doesn't require eternity to matter. The universe began in a low-entropy state where information was highly correlated. As expansion proceeds, that information spreads and correlations weaken. The universe is heading toward a state of informational exhaustion, not destruction, but a kind of cosmic silence. A universe where information still exists, but it's completely inaccessible, uncorrelated, and useless. Nothing can be known, nothing can be predicted, nothing can change. Time itself loses its operational meaning. But this future is incredibly distant. In the meantime, information flows. Stars encode nuclear histories. Planets encode chemical histories. Life encodes evolutionary histories. Civilizations encode cultural histories. We build libraries, archives, and telescopes are attempts to preserve information against the relentless tide of entropy, and entropy always wins, eventually. But this doesn't invalidate the attempt. It defines its context. Knowledge isn't about permanence. It's about transmission, about passing patterns forward, even if only for a moment. This perspective reframes the purpose of science itself. Science isn't about finding some final, ultimate truth. It's about compression. It's about finding simple rules that describe complex patterns. This is the heart of information theory. A good theory compresses a vast amount of data, explaining much with very little. Physics, then, is the ultimate compression algorithm. Some physicists even propose that reality is a computation. The universe computes itself, evolving from one state to the next as physical laws are applied, updating its own information. It's a controversial idea, but an intriguing one. If the universe computes, then it must have limits on information density and processing speed. This means reality might have a resolution. It might not be infinitely detailed. At the most fundamental scales, space-time itself might be discrete, not continuous. This aligns with modern approaches to quantum gravity, like loop quantum gravity and string theory, which all try to describe space-time as an informational structure. But the more physics reduces everything to information, the more it challenges our intuition. If everything is information, what is real? The answer is both unsatisfying and precise. Relationships are real. Correlations are real. Patterns are real. Substance is secondary. This isn't a new idea. It echoes ancient philosophy, but now it's mathematical, testable, and constrained. Information isn't just an abstract concept. It has limits, costs, and consequences. This framework can also dissolve some existential anxiety. Meaning doesn't require permanence. Information patterns exist briefly, but they exist, and that is enough. A melody is real while it's being played, and then it fades. Life is like that. So is knowledge. So is the universe itself. This perspective doesn't answer why there is something rather than nothing. It reframes the question. Nothing may not be a stable state. Information may spontaneously arise from quantum fluctuations. Structures form. Reality happens. Not for a reason, but because the rules of physics allow it. This isn't comforting, but it is coherent. And coherence is what physics seeks. And if reality is relational, then what is our role? Are we observers, participants, processors? Do we matter on a cosmic scale, or only locally? The universe doesn't assign roles, but physics suggests one thing clearly. We are not outside the system. We are inside it. Every observation we make is internal. Every measurement is an act of participation. We are not watching the universe. We are something the universe is doing. This doesn't elevate us, but it situates us right here, inside this grand, unfolding story of information to arise. Chemistry persists long enough for life to begin. Life persists long enough to develop memory. Memory persists long enough to build culture. And culture persists long enough to create science. Each layer is built upon the last. None of them were guaranteed. All were conditional. Meaning emerges simply because some patterns last, while most do not. The universe is overwhelmingly filled with transient noise. Quantum fluctuations appear and vanish in an instant. Particles form and decay. Most configurations of matter and energy leave no trace, but some leave echoes, and those echoes interact, reinforce, and amplify each other. This is the birth of structure, and meaning is just structure that influences what happens next. I know this definition can feel a little uncomfortable. It strips away the romance and the poetry we usually associate with the word meaning. But it's also incredibly powerful. It explains why meaning feels so personal and local, why it's always tied to a specific context, why it can change, and why, eventually, it can fade away. Meaning exists wherever a pattern connects the past to the future. This is where entropy comes in. Entropy, the tendency for systems to become more disordered over time, is the great dissolver of patterns. As entropy increases, persistent patterns become rarer. It's not that they become impossible, just much, much harder to maintain. This is why we see bursts of complexity that appear for a while and then disappear. Let's think about life again. A living organism is a masterpiece of pattern persistence. It actively maintains its internal structure, fighting against the constant pull of entropy. How? By exporting disorder out into its environment. You could say that life is a meaning engine. It's a process designed to preserve patterns, genetic information in DNA, neural information in a brain, behavioral patterns passed down through generations. These patterns directly influence future state survival, reproduction, adaptation. Meaning emerges naturally from this process, not because the universe intended it, but simply because the laws of physics allow it. Meaning isn't imposed from above, it's emergent from below. This same logic applies to something as profound as consciousness. Consciousness feels special, like it's separate from the physical world. But from a physics perspective, it's a process, a dynamic, intricate pattern of information being integrated in the brain. It only persists as long as the necessary conditions are met, while energy flows through the system, while delicate chemical gradients are maintained, while its physical structure holds together. When those conditions fail, awareness fades. This isn't to reduce consciousness or diminish its wonder. It's to ground it in reality. Consciousness is absolutely real, but it's conditional and temporary, just like everything else. This reframes our deepest fears. So much of our anxiety comes from a desire for permanence, for things to last forever. But physics offers no such guarantee. What it does offer is continuity. Patterns propagate. An idea can pass from one mind to another. Knowledge can accumulate over generations, even if only for a brief cosmic moment, and that's enough. Meaning doesn't require eternity. It just requires connection. So, is there meaning at the cosmic scale? Well, not in the human sense of purpose, but there is structure. There are patterns that have persisted across billions of years and unimaginable distances. The great filaments of the cosmic web, the shapes of galaxies, the fundamental laws and symmetries of nature. These are physically meaningful because they shape everything that is possible. The laws of physics are themselves the ultimate, persistent patterns. They are meaning at the deepest level, not a purpose, but a constraint. This distinction is crucial. Purpose implies an intention, a goal. Physics doesn't imply intention, it implies consistency. The universe behaves in a reliable, predictable way, and that reliability is what allows us to make predictions. Predictions allow us to plan. Planning allows us to survive. Survival allows us to reflect. And reflection is what creates questions. Those questions lead to science, and science feeds back into our understanding of the universe. This entire loop is remarkable, not because it was destined to happen, but because the conditions of the universe were such that it could happen. This brings us to a subtle but important shift in thinking. Meaning is not something you go out and find, like a hidden treasure. It's something that is enacted. Every observation you make, every measurement taken in a lab, enacts meaning by creating a correlation between states, by leaving a record that influences the future. The universe isn't meaningful by default, but meaning appears wherever information is being processed. This also explains why meaning feels so subjective. It's because it's always local. Different systems care about different patterns. A supernova is incredibly meaningful to a nearby solar system, but it's completely irrelevant to a galaxy on the other side of the universe. Meaning is relative, but it's not arbitrary. It's always grounded in physical interaction. This perspective doesn't diminish human significance, it relocates it. We are not cosmically important in the grand scheme of things, but we are incredibly, profoundly, locally meaningful. We are nodes in a network where information has become fantastically concentrated. We are processes that have evolved to reflect on the very patterns that created us. This is a rare thing in the universe. Not necessarily unique, but rare. And that rarity gives a certain weight to our existence. Not a cosmic weight, but an experiential one. This viewpoint also dissolves nihilism. Nothing needs to have an eternal, ultimate meaning in order to matter. Moments matter simply because they occur. Patterns matter because they have influence. Your experience matters because it exists. Physics doesn't strip meaning away from the world. It just shows us that it lives in the process, not in some grand cosmic blueprint. And what about morality? Morality isn't written into the fabric of the universe as a cosmic law, but it emerges naturally wherever conscious agents interact. It emerges where actions have consequences, and where those consequences matter to the systems involved. Systems that can experience well-being or suffering. In a sense, morality is a kind of local physics that doesn't weaken it, it grounds it. Responsibility emerges because our actions create ripples that propagate through the world. Meaning arises in those causal chains. So, let's consider one final idea. If meaning is fundamentally about patterns that persist, then the scientific endeavor itself is a form of meaning-making. Science is the process of compressing vast amounts of information about the universe into elegant, predictive patterns we call laws. Science is the universe, through us, developing a more efficient understanding of itself. This self-reference isn't mystical, it's reflexive. Brains evolved to model their immediate environment. We are the universe, modeling itself, locally. This doesn't imply a purpose, it just implies a capability. The universe permits systems that can reflect its own structure. Those systems exist for a brief time, and then they vanish. But while they exist, that reflection happens. And that is profound enough. We don't need transcendence. We can have meaning without permanence, purpose without a designer, and value without a guarantee. This is the quiet, honest truth that physics points toward. It isn't bleak, and it isn't comforting. It's just honest. Thanks for watching. If you enjoyed this journey into the physics of meaning, please consider subscribing for more explorations into the biggest questions.